Okay, so it's 5 o'clock and I'm going to start recording. And I'm going to go over, just do a quick review of some of the material that we went over last time and then start some new material. Remember that there's the basic idea of parallel transport, where you transport a vector along a curved surface, and you do so in such a way that in the frame of the surface, or in the tangent plane of the surface, the vector is always pointing the same way. And the illustrations are here. This red vector starts, if it starts on the equator, it's pointing directly north, though not at the North Pole, but in a direction that's parallel to the line from the South Pole to the North Pole. And then as you transport it in a parallel way, that's so that its covariant derivative vanishes. And the condition here was that the covariant derivative dotted into, or the change in the vector dotted into the tangent vector, or equivalently dotted into the cotangent vector, gives you zero. And that gave us two equations, one for the transport of a contravariant vector, the other transport of a covariant vector. And so for the covariant case, I hope you're not going dizzy here from the way I'm moving things so rapidly on the screen. Anyway, the equation for the parallel transport of a covariant vector is that U is just a distance along the path, that this is equal to the Christoffel symbol of the second kind dotted into the covariant vector times the change there in the coordinates. And so consequently, the change in the ith component of the covariant vector V, due to the parallel transport of the covariant vector around a loop, is given by an integral like this. And so the way to evaluate that and get an estimate of what curvature is like inside a very tiny square is you approximate let's see if I can, let me see if I can get this tap to connect. Turns out tap with a finger is good enough. So in other words, we're going around a little square here. Here's x0, and it's of size A. And so we expand the Christoffel symbol in terms of its derivatives and the covariant vector in terms of its derivatives, and we multiply the thing out, and we keep only terms linear in x minus x0. The zeroth term would be just the integral here of a constant times dxl. Well, that's identically zero, because if you go around a closed loop, you get back to the same point. And so what you have left is this. And I showed last time explicitly that that the integral of the nth coordinate, the difference between the nth coordinate and the center of the square, or the nth coordinate at the center of the square, integrated around the surface, it's plus or minus the area of the surface. And So what one gets, and it's anti-symmetric, as that's what epsilon is here. It's epsilon 0, 1 is 1, epsilon 1, 0 is -1. And so what you get is plus or minus a squared times this. And that then, after you explicitly represent this anti-symmetry, you get the NL term minus the LN term. And what's in here is Riemann's curvature tensor. And you can then, and that's something that formally has 256 entries, but in fact is only has 20 independent entries because of a variety of symmetries. And you can contract this, you can raise one index, or actually I think the way we derived it, it already had an index raised. You can then trace over that index and you get the Ricci tensor, and you trace again, you get the curvature scalar. And this is just a section that says that what is the invariant volume element is square root of the absolute value of the determinant of GIK, G lower IK, d4 x. And here we went through the divergence of a contravariant vector. And what happens is there's a formula that's, it's a little, in other words, formally, if you're doing the covariant divergence of a contravariant vector, you get this expression. But it turns out that that has a form that can be written more simply in this way. And so when you apply this to Maxwell's equations, you can see that that Maxwell's inhomogeneous equations can be written this way. And the covariant derivative of the energy momentum tensor also takes a somewhat simpler form. I see here there's a comma missing. So let me make a note to fix 11.111. And the covariant Laplacian, so you're taking the covariant derivative of a contravariant vector. You then have, if you work it out, you have a bit of simplification, and you get, this is a double trace or a double contraction. You're summing over K and I. We went through, I simplified the discussion of stationary action for the class notes. Actually, I think I'm going to also change the book and toss out the part that was really overly complicated, unnecessarily complicated. What one finds then is that the equation for a particle in a gravitational field represented by the Christoffel symbol and an electromagnetic field, this is F, this is the E and B fields, which are, FIK, the Maxwell tensor, and with one index lowered. And it then looks like this: mass M, charge Q. So the mass enters only it simply measures the sluggishness of the response of the charge to the electromagnetic field. And once again, if you write the action for a current in an electromagnetic field, this is the electromagnetic field action, this is the interaction, this is the invariant volume element. You then get, from the principle of least action, you get Maxwell's equations in generally covariant form. The only reason why I went through the covariant divergence and so forth, the covariant Laplacian, is just to get you the formula for a scalar field in a gravitational field. So that looks like this. And in a little bit more simply, it looks like this. For weak static gravitational fields, we drop the derivative terms that refer to that are proportional to velocities. Here, remember, ui is dxi dτ, and for low velocities, dτ is dt. I can see here that I'm trying just to get rid of this one thing because it there. And so then the geodesic equation becomes this form dur dτ is this expression here, and because the field is static, we can neglect some time derivatives, and in particular the ones that occur in the Christoffel symbols. So we're going to drop these two terms. We just have that term, and then it turns out that this is just the gradient of the, apart from a factor of -0.5, it's the gradient of G00, which is a constant, plus H00. And so one has this as the field equation. And for slow motion, as I said, dτ is dt. And so you just get down to dx, well, just Newton's equations for gravity, at least when you then recognize that G00 is -1 plus H00 and so forth. So you just get Newton's equations. For time dilation, back on Tuesday, I was, the equations were correct, but I was confused in the interpretation of them. The key thing is that the interval between ticks of a clock at r in a gravitational field due to a mass m, if you're a distance r, clock's a distance r from a mass m, is related to the time between clocks for a clock at rest outside the gravitational field. Both clocks are at rest, but one is far from the gravitational field and the other is a distance r from this mass m that the point here is you can imagine this, imagine that instead of a clock, you have your heart and it's beating. And so here it's beating at a certain rate out in empty space. But if you're near that big mass, then this dt becomes a small interval, like a tenth of a second or a second or something, and you're dividing by a very small number as this approaches unity. And so the time between heartbeats is huge. And well, what does that mean? That means that the person ages almost not at all. His biological clock, as well as his physical clock, slows down in the gravitational field. So that's the meaning of this. The dt actually increases, but that just means that the time between physical events is greater. And I mentioned these three examples here. If any of you have not seen Interstellar, I recommend it highly. The first measurement of the redshift of light in a gravitational field was done using a staircase at Harvard, and I guess it must have been a laser at the time, and a laser, and what was new then was the Morse-Bauer effect. The redshift of light from the sun is about 2 parts per million. Okay, so Einstein's equations, I think we'll focus a little bit on these today. And first of all, the Einstein-Hilbert action, there's a constant out in front. Then this is the invariant volume element, and this is the curvature scalar. So it's basically the integral, the Einstein gravitational action is the integral over space-time of the curvature. But when we do the integral over space-time, we use an invariant volume element. And R, by definition, is the fully contracted Ricci tensor, RIK. And remember, the Ricci tensor was the curvature tensor with one index raised, and you trace over that index or contract that index. There are a couple of technical things in in applying the principle of least action to this, and remember, what we're saying here is that the first order change in the Einstein-Hilbert action due to a small arbitrary change in the metric at some given point, an arbitrary point in space-time, should be of second order in that small change. And to first order, the change should vanish. And so what we do is we first look at what the change of the, so the change here, oh goodness, I just lost the ability to, oh God. So let's see if I can, so yeah, change in square root of G. Well, this is the change in the absolute value of the determinant of, say, GIK like that, and then square root. And so this is 1/2 the square root of G in the denominator times the change in the determinant of G. So it's 1/2 this to the minus 1/2 change in right, I have right, it's written a little in a bit of a funny way here, because it's written as 1/2 determinant of G divided by G, but G is just determinant of V apart from absolute value times square root of G, and then the change in the determinant of G. So that's what this expression is. The reason for determinant of G over G in there is to take care of the minus sign or the absolute value sign. And then the change in the determinant, well, that's this formula here that we derived back in chapter 1, namely that the change in the determinant is the determinant times the trace of the change in the matrix times the inverse of the matrix. And the inverse of G lower is G upper, and the change of that is this, and then this is the trace. And now what you've got is one of these cancels one of those, and apart from an overall, well, it's also true that the change, this product, matrix product here is just a Kronecker delta, delta IL. And in other words, delta IL is equal to GIK, GKL. And so obviously its variation is going to be 0. And so that's equal to the change in the upper times the lower plus the upper times change in the lower. So we can shift from this to this, but we get a minus sign. And so altogether then, the change in this structure here is, it's an RIK times the change in G upper plus G upper times the Ricci tensor times the change in square root of G, and then G upper times square root of G times the change in the Ricci tensor. So combining those together, we get the really the curled, I don't know, I guess in the brackets, the ordinary brackets, times square root of G times the change in the inverse metric plus another term. This other term we're going to throw out because we're going to show that it's a surface term. What one does is one says, well, this change here is a difference of two Christoffel symbols, and one can rewrite that as well, it's the variation. I'm just rewriting it in the standard way, and then we have this expression here, and changing the names of dummy indices, we get to write this as something like a divergence. Now, if we had nothing more, if we didn't have a square root of G there, we could just say, well, and I'm talking about this square root of G, we could say this is a total divergence of surface term, we throw it away. Well, because of this square root of G, we have to do a little more work. I'm going to skip the work here. What one does is one shows that in effect we can replace this ordinary derivative by a covariant derivative, and then we can write this in terms of a divergence of the term involved with the square root of G. And there's a total divergence. So we've absorbed the square root of G, and so then we can throw that away. In any event, the point here is that the root to Einstein's equations from this action is, you first of all write this curvature scalar as a trace of the Ricci tensor or contracted Ricci tensor. Then you take you write the variation as an important piece plus a term that turns out to be a surface term. And then what one has is that the variation of the action, apart from the surface term that you can neglect, is given by this important term of the Ricci tensor minus the curvature scalar times the ordinary tensor times minus a half times square root of G, inverse metric, change in the inverse metric d4 of x. This has to vanish to first order in this term, and consequently this is equal to 0. So these are Einstein's equations in empty space. And of course, they have as conclusions or as consequences that the curvature, that empty space is not curved and the Ricci tensor vanishes in empty space. Well, it turns out that the energy momentum tensor is always defined, and when I say always, I'm excluding the possibility of new physics that might take an exception to this equation. But in general, the change in the action of the matter fields due to a change in the metric or in the gravitational fields is always given by this expression. It's the energy momentum tensor square root of G, change in the inverse metric d4 of x, and if we rewrite it, it takes this form. And here, of course, I'm just I'm using the change in the inverse metric is related to the change in the lower metric in this way. And now the the principle of least action, which is that the change in the total action vanishes to the lowest order. That gives us that the gravitational part is equal to the energy momentum part. And so these are Einstein's equations, and this is the basis of all cosmology that we do. Let me see. Oh, I see. I've lost complete track of time. It's only 5:25, and I've almost gone through everything that I intended to go through. So this is rather strange. If you take the trace of both sides, you see that here we're taking the trace of this, you get the curvature scalar. When you take the trace of this, you get 4, and so you get 1 minus 2 times r, and so that turns out to be minus r. So that gives you this minus sign here when you take the trace of the right-hand side. And once you know that r is related to the trace of the energy momentum tensor in this way, you can rewrite this equation as Ricci tensor is g times energy momentum tensor minus the trace of the energy momentum tensor times the metric of space-time. So this, of course, tells us this explains why why the Ricci tensor and the curvature scalar vanish when the energy momentum tensor is 0. Now, we must realize, though, that the energy momentum tensor can in fact be dominated by dark energy and secondarily by dark matter. And the stuff that we've seen in the telescopes, the various stars and planets, that's only a small part of the energy momentum tensor. So that's so to speak, put humanity in its place in the scheme of things. And it's somewhat embarrassing for physics. It should, it should tell governments that they should really fund research in physics, because the physics that we know about is just a tiny fraction of the physics that is. And there could be huge practical implications of understanding what dark energy and dark matter are. Anyway, a little more about the energy momentum tensor. Well, this is, I said to you earlier that this is somewhat like going into the weeds. The change in the energy momentum tensor turns out to be this, I think, we've already seen that. But working through this, I'm going to skip it. Working through this, what you find is that the covariant derivative of the energy momentum tensor vanishes, and that covariant derivative is of this form. This is something that we went through, or at least flew over in earlier lectures. Certainly in the class notes. In the absence of gravity, that is to say, in flat space, this equation, the gamma vanishes, and this equation is just this equation, just that the divergence, the 4 divergence of TIK vanishes. That's the conservation of energy and momentum of matter fields. And what one has, though, what one can show more generally is that if you take the energy momentum tensor of matter fields and the analog, its analog for gravity, which is a pseudo tensor, that the divergence of this vanishes, and it vanishes because the action doesn't depend upon an external space-time point. And so one has conservation of energy and momentum of matter plus gravity. The awkward aspect of this is that the analog of the energy momentum tensor for the gravitational field is not a tensor, first, and second, that is to say, when it doesn't transform simply under general coordinate transformations. And secondly, that the spatial integrals of energy momentum for the gravitational field often diverge, or you do the integral and you find it's a surface term, but it's not zero. You see, when we throw away surface terms, in particular, when we're like doing the principle of least action, we toss out a surface term. That's because we can choose to say that we're considering a variation at a particular point in space and time, and we're saying that the action should change only to second order in this small change of the fields in a particular point of space and at a particular time. And so then, of course, any surface terms that can be neglected because we're not changing anything at infinite distances. And on the other hand, when one computes the energy and momentum of in the context of general relativity, one gets surface terms that represent energy or momentum and can't be thrown away because they're not just arbitrary changes at individual points in space-time. All right, well, that was a long digression here. When one does cosmology, of course, one simplifies the treatment of matter dramatically, and in particular, the model that is used most commonly is that of a perfect fluid. And the idea is that if you're in the rest frame of this fluid, it looks the same in all directions, it doesn't conduct heat, and there's no viscosity. And so it's anyway, that's the concept of a perfect fluid. In fact, I wonder why the concept of zero viscosity is appropriate, because in fact, if you although you can imagine that stars far away aren't affecting each other very much, they do have gravitational fields and they drag each other. And so if you have a certain part of the universe and you have a star come through, although it doesn't push, it's not like moving your finger through molasses, it's instead that as that star goes through, it does drag all the other stars with it a little bit. So I wonder whether this perfect fluid model is valid. Of course, to a very good approximation, a star going through a galaxy is not going to disturb the galaxy very much unless it hits other stars. Anyway, the energy momentum tensor is of this form. It's the pressure times the metric of space-time, and then it's a product of the four velocities times the mass density. Rho here is the mass density, not the energy density, and this is the momentum. This is the pressure over c squared. And so if we put that in, if we say that is Tij or Tik, we put it into Einstein's equations, we get Rik minus half Gik. R equals 8 pi G over c to the fourth Tik, and then that's 8 pi G over c to the fourth times this thing here. And there are various special cases. One special case is that the energy momentum tensor due to the energy density of the vacuum And you might say, well, this is entirely trivial. And that was what people thought until about the year 2000. But let's, when dark energy, of course, was discovered. By the way, Ries's first name was Adam. It was Adam Ries, who led one of the teams, the Space Sciences Institute team from the East Coast to discover dark energy. Saul Perlmutter was leading the Berkeley, the West Coast team to discover dark energy. I'm petting my dog here. That's what I'm doing. Anyway, for the energy density of the vacuum, it turns out the pressure is minus c squared times the mass density. And I said to you last time, the reason for that is that if you increase, for an ordinary system, if you have a gas and you increase the volume, what happens is the way in which the volume increases is that the pressure of the gas molecules push the sides out, and the work that they do means that they lose energy. So the pressure then is positive, and the change in energy with respect to volume, the energy of the gas inside the box decreases. Whereas when you're talking about space having an energy density, then if you increase space, the energy density inside your box increases, and consequently, the pressure is negative. So that's why there's a minus sign here. The c squared requires a further argument, and I'm going to skip it. So what we have then is, if P is minus c squared and we substitute in here, we get that the energy momentum tensor is minus c squared times the mass density. So this is minus the energy density, in fact, times the space-time metric. And so that's a nice way to think about this, that the energy momentum tensor due to dark energy is minus the energy density times the metric of space-time. And so anyway, you might have, as I said, before 2000, we thought this was zero. And now we realize that it's most of what's going on. And in fact, as we'll learn in maybe later today, or if not Tuesday, when you do actual cosmologies, do the best we can with modern cosmology, what we find is that the universe is expanding to a state already something like 60% of the energy density is dark energy. But as the universe expands, more and more of the energy of the universe is going to be dark energy, the energy of empty space, because space is going to become more and more empty as the stars go far and far apart from each other. And so one is getting to a situation where this is an accurate description of the energy momentum density. Now, you might say, well, what about this Big Bang? What we know about the Big Bang for sure is that the universe used to be much smaller, our universe used to be much denser, much more compact, much hotter. And so it's natural to extrapolate back, but the further one extrapolates back, the more mysterious, the less we know about the physics. And of course, what we know about the physics is essentially Zippo, since we don't know what dark energy or dark matter is. So we're sort of whistling in the dark here. But the presently commonly accepted most popular theory of what goes on at or before the Big Bang is a period of inflation. And this is very much like what we're talking about here, namely that that empty space can, or in a sense, empty space can have an energy density. The idea in the case of inflation is that there can be a field. The space is not really empty. It has instead a field. Of course, there are fields all the time in empty space. But anyway, here we're imagining that there's a field whose potential energy is huge in a certain region of space at a given time. And when that happens, you see what you have is as over here, the pressure is minus is negative, and absolutely huge. The idea here is that the energy density of space at this particular time in this particular place is absolutely extraordinary in size, and consequently the pressure of expansion is absolutely huge, and so space expands in a super fast way. And this was called inflation by a physicist who was then at Stanford. He was a postdoc, I think, at Stanford, and later became a professor at MIT. Very nice man. As usual, I forget his name. I think he Zoomed us a colloquium a couple of years ago. Anyway, that's called inflation, and he named it inflation because he discovered it in the late 70s or maybe 1980, when inflation was twice what it is now, and so inflation was like 20% a year or 18%, and Jimmy Carter was president, and he appointed Paul Volcker as secretary of the, not secretary, was he? No, he was head of the Fed. And he said to Volcker, do what is right for the economy according to traditional economics, and that was to raise interest rates. And so Volcker raised interest rates in a way that had never been raised before, and just slammed on the brakes and stopped inflation. And since then, we've had 40 years of no inflation until recently. Things went off the rails because of the pandemic and stupid foreign policy and so forth. So inflation might have occurred. In fact, most people think it did occur. And what happened then was you had a fluctuation of a scalar field to an absurd value, just a quantum fluctuation in a very tiny region to an absurd value. But once that happened, that region expanded like nobody's business because of the negative pressure associated with a high energy density. And so that tiny region expanded like crazy, and it expanded so fast that the scalar field didn't have time to go down to its normal value. It just stayed at that high value. And so you had then a macroscopic region of space that had an absurdly high energy density. Then that energy density, that is to say, the scalar field then found its way down to zero, and when it did so, it released all of its potential energy as radiation, and that's what we call the Big Bang. So that's the prevailing theory. The way I explain it, some people, I think, stupidly think that well, never mind that. There is another theory, however, which I hope will be explained to us by Paul Steinhardt of Princeton, who promised to give us a colloquium in early May. And the idea there is a bouncing universe, namely that the universe used to be very spread out the way it is now, but it contracted over billions of years to a very high density and bounced. And the Big Bang is the very hot bounce. So we don't know which is true. Both are plausible, well, remotely plausible. So anyway, well, all of that was just to show you that Einstein's equations with Tij equal to just Gij times a constant is not that crazy. In fact, it is what the universe was most of the time. In fact, if we take the bouncing universe seriously, then for most, if we look on a scale of hundreds of billions of years, or say a scale of 1 trillion years, the only thing that counts is dark energy. Matter is just kind of a little bit of dust or pollution on this scheme. And what happened was the dark energy collapsed, bounced, and has been re-expanding for 14 billion years. And in another 10 or 20 billion years, the matter will be totally, even dark matter will be ignorable. It's a first approximation, even second order. So gravitational waves, well, in empty space, and empty in quotes, in empty space, the metric is the ordinary metric of space-time, which is, let me just, and since we skipped special relativity, let me change the color also here. Let me go to, say, red. Eta, well, let me write it there. Eta is -1, 1, 1, 1, and zeros everywhere else. This is the metric of flat space-time. And so the actual metric is eta, the metric of special relativity, plus a tiny fluctuation due to gravity. And if we work through that to first order, then the affine connection, well, the affine connection is this, but these are derivatives. So the derivatives are already first order. And so in G inverse, we have to use eta. And then to first order here, we just have the H term. And the Ricci tensor is then a contraction like this. Well, the gamma term is second order, so that goes. So we just have the derivatives of these, and it's an antisymmetric combination like that. So that's the Ricci tensor. And if we combine this with this, what we get is something involving a lot of second derivatives. So these are second derivatives. The Ricci tensor then is all kinds of second derivatives of the change of the first order departure of the metric of space-time from the metric of special relativity or a flat space. And it turns out that one can choose coordinates, which are called de Donder's harmonic gauge, which is that a certain divergence of H is just equal to the derivative of a contracted form of H. Anyway, in this de Donder's gauge, this complicated expression just turns into basically a full Laplacian on the change in the metric vanishes. So this is the wave equation, and that describes gravitational waves. And the LIGO collaboration in 2015, which is now 7 years ago, detected the merger of two black holes of 29 and 36 solar masses, and the collapse liberated 3 c² times the mass of the sun of energy when they collapsed. This was gravitational energy released. Now you might say, well, that's an enormous amount of energy, but in fact, it did almost no damage to any nearby stars because the gravitational force is so weak. They also, and this was way back in, this was as of 2019, about 3 years ago when I looked up the upper limit. They had set an upper limit of the mass of the graviton as, or the energy of a graviton as being less than 2 times 10 to the minus 25 electron volts. By comparison, the mass energy of an electron is 500,000 electron volts. By now, they've detected about 100 black hole mergers. And so this is becoming a really important form of astronomy. And this may resolve the issue of whether our universe is a bouncing universe or an inflating universe. The Schwarzschild metric is a solution of Einstein's equations for empty space for the case in which there is a point mass, or to put it differently, you solve Einstein's vacuum equations, but with the boundary condition that inside a certain region, there's a certain amount of mass. And so you're a distance r from a mass m. And that's the, this is called, often people call this the line element. I'm not quite sure why, but anyway, it's the square of the separation, the invariant separation. And this is just the ordinary r squared d omega squared. And then we have these terms. And of course, what's remarkable here is that this guy here can approach unity, and then things can be quite spectacular. The proper time of a clock at rest at r in Schwarzschild's coordinates is given by this, and it's less than that measured by a clock at rest far from it. So I've switched in this description here the dTau and the dt, and oh, wait a minute, no, that is dTau is the, so anyway, this is time between ticks. So let's try to get this straight. So dTau less than that. So here I've got dTau equal to dt. That was, so that I need to change. That's a silly way to express things. All right, let's put it this way. The time between ticks for a clock near a black hole is huge. And that time, as you get close to the black hole, or what's called the Schwarzschild radius, where this quantity becomes unity, the dt becomes, the time between ticks becomes infinite. And so to say it again, the dt, which is time between ticks, is the dTau at infinity divided by this 1 minus 2gm over c squared r. And so this goes to infinity, which means the time between ticks is essentially infinite. And so that's why those guys on Miller's planet, their hearts and their biology slowed down so much that when they came back to Earth, the people they knew were all quite old. my age. Anyway, a physicist at Princeton, whose name I can't remember, devised the term or invented the term black hole. He invented he invented at least one other name that was amusing and that became standard physics usage, but I forget what it is and I forget his name also. He gave a talk at UNM, but that was like 30 years ago. Anyway, suppose we have an uncharged, static, spherically symmetric star mass m, and it collapses to within a sphere less than its Schwarzschild radius. Now, this is, one needs something special to have this to happen, because in the case of the sun, the Schwarzschild radius is only about 7 times 10 to the 5th kilometers, and the sun is vastly bigger than that. What Hawking showed back in, well, this is a long time ago. This is 25 plus 22, which I guess is 47 years ago. My God. He showed that that a black hole would not be actually black, but instead would radiate. And it's that the intense gravitational field causes radiation. And the temperature there is a remarkable combination of physical constants. And it's all, not only is it remarkable, but it is surprising in that you'd expect that the temperature would be higher if black hole were more massive, but it's the opposite. It's that the temperature is inversely proportional to the mass of a black hole. So it's really quite remarkable. And so what actually happens is that if you have a big black hole, it radiates, but it radiates very, very, very little, which of course is why no one suspected what's called Hawking radiation until 1975. So if you have a big black hole, it radiates, but very, very little. And then in billions of years, maybe trillions of years, I don't know, haven't done the calculation, it radiates away its energy if it doesn't absorb more matter, and the mass decreases because it loses energy. And as the mass approaches zero, though, the temperature goes higher and higher and higher until it goes pop. And so all these black holes eventually end in flashes, where they're at very, very high temperatures. So if you have a region of empty space where the pressure is P and there's no pressure and no chemical potential, the change in the internal energy is, by definition of the thermodynamic variables, du is TdS, where S is the change in the entropy. So the change in the entropy of a black hole at temperature T is ds. Here's the change in the energy, and if you rewrite it, you get this expression here. And if you integrate, then you get a formula for the entropy of a black hole in terms of its mass, and you get that the entropy of a black hole is the integral of m dm. Of course, what we're using here is this expression for the temperature. So we have ds is c squared dm, that's du, or change in the energy. We divide by t. Dividing by t means we multiply by m. So we have m dm, apart from constants. And when you integrate m dm, you get m squared over 2. And that changes 8 to 4. So what you get is that the entropy of a black hole then is given by, it's proportional to the squared mass, and in terms of the squared mass actually is related to the area. And so you get that it's basically the entropy is the area of the black hole. And what you have to do, though, is there's a constant out in front. And the constant out in front turns out to be this expression here. And that's because we're rewriting m squared in terms of the area of the sphere at the Schwarzschild radius, and so that's why g goes in the denominator there. The rate of energy radiation is, of course, it's going to be t to the fourth times the area times the Stefan Boltzmann constant, or Stefan's constant, and that turns out to be this quantity here. And if you then integrate, you find that the black hole is entirely converted to radiation in this time. So this is what I said was billions of years. It's actually given by this formula, and well, it'll be interesting to know what that is. I haven't done that calculation in a long time. I think I'll assign that as a homework problem to compute how long a black hole of a given mass, say 60 times the mass of the sun, how long it lasts. It obviously lasts a length of time proportional to the cube of the mass. The reason for that, of course, is that, remember, the temperature of the black hole is inversely proportional to the mass, which is, again, very surprising. You'd naively expect the opposite. When you have a rotating black hole, this was worked out by Roy Kerr, and it's quite interesting. I'm not going to go through certainly not the derivation, and I don't think I've ever been through the derivation of this, but one finds the following, that a rotating black hole drags, or rotating mass more generally, drags nearby masses along with it. And in particular, the daily rotation of the Earth, and the Earth is by no means a black hole, the daily rotation of the Earth drags satellites to the east. Remember, the sun the Earth rotates toward the east, which is why the sun rises in the east, sets in the west, by tens of meters per year. So that's a macroscopic effect due to the rotation of the Earth, and this is called frame dragging, and in some cases, black holes can be dragging the matter that gets close to them to speeds approaching the speed of light. So whereas the Earth drags things by tens of meters per year, which is pretty slow, a black hole that's rotating rapidly can drag stuff around it and make it approach the speed of light, which would then, of course, radiate like nobody's business, to the extent that they're charged. And even ordinary neutral matter, of course, is composed of charged matter, and so it would be radiating, even though it's macroscopically neutral. The commonplace cosmology, or the standard cosmologies that have been accepted for decades, but which may get a little tweaking in the next decade or two. I hope they do. These are called Robinson-Walker cosmologies, but they really should be called Friedmann-Lemaİtre-Robinson-Walker cosmologies, because Lemaitre, who was a Belgian priest, I think, and Friedmann made huge contributions to cosmology. And so here, as I said, astrophysical observations tell us, or astronomers tell us, the universe extends to at least 46 billion light years in all directions. It's flat or very nearly flat. The last time I checked, the observations, astronomical observations, have not indicated any observation of curvature of the universe, as opposed to curvature of space-time around a black hole. The cosmic microwave background radiation is isotropic to 1 part in 10 to the 5th, apart from, of course, a Doppler shift due to the motion of the sun. The sun is moving at 370 kilometers per second, which is pretty fast, and it's in the direction of the constellation Leo. I have no idea what that is. These microwave photons in the CMB are photons that first got to travel macroscopic distances about 380,000 years after the Big Bang, when the known universe had cooled down, when the Big Bang had cooled down to below a temperature of 1 electron volt, or substantially below 1 electron volt, so that most of the hydrogen was neutral, and all the helium virtually was neutral. And so the universe was a neutral gas, unionized, and so photons could go through it. And these are the photons that we're seeing. The photons that were emitted only 300,000, say, or 350,000 years after the Big Bang, these photons were traveling through a plasma of ions, or free electrons, free protons were so common that the photons would scatter, and the density of the universe was higher, and so they would scatter like crazy, and they couldn't go any distance in a straight line, so we don't see them. They've been scattered. As far as we know, the universe is homogeneous and isotropic, and of course that makes for a very much simpler cosmology. There are only 3 maximally symmetric spaces of 3 space dimensions, and these are Euclidean space, the 3-dimensional sphere, and a hyperboloid called H3, the supersymmetric one, and this is a 3 surface that's embedded actually in a 4 space with 1 time dimension. Anyway, the line elements of these, or the invariant distances of these, are given by dr squared over a certain quantity, which can become 0, and r squared d omega squared. And these simplest cosmologies, in other words, since we haven't seen any departure from isotropy and homogeneity in the universe on large scales, what we say is, well, our cosmology should be one of these maximally symmetrical 3-dimensional spaces times time. We just put time in the most trivial way, minus c squared dt squared. And then what occurs here is this metric, but times a scale factor called a of t. The astronomers choose weird units for a of t. They have a at the present time equal to unity, which of course makes things simple for their observations, which are done at the present time, but means that A at the time in which, the time of first transparency, 380,000 years after the Big Bang, A then would have been microscopic. It would have been 1 part in 1,000, something like that. Anyway, the resulting metric then is I'm calling it the FLRW metric, and it's of this form then. It's diagonal, and time is treated in a trivial way, the most simple way possible, and then this is a maximal asymmetric 3 space. And as I said earlier, we've not seen any curvature in astronomical observation, so we can set k equal to 0, but of course we shouldn't, because we future observations may show us that the universe is either open, k equal -1, or closed, k equal to 1. The inverse metric, of course, is also diagonal, and it has a very simple, obvious form. And so now one can then go about computing the Christoffel symbols, and you can compute them directly. It's not that hard. You would just differentiate the various these terms of the inverse metric. And if you're choosing r, theta, and phi, it's pretty obvious how to get these Christoffel symbols. Another way to do it is to say, well, we derive the geodesic equation, and we say that this has 0 first-order variation, and then what we get is we identify these Christoffel symbols as whatever we get from doing that variation. I don't know if that's, I mean, in retrospect, I'm wondering whether that is the simplest way. When I wrote the book, I thought that was the simplest way. But looking back at it, if you're differentiating in in XYZ coordinates, then this is kind of complicated. But we're talking about, we can use t, r, theta, and phi coordinates, and then the derivative. These things are very simple. So I don't understand why I thought it was clever to do these things this way. In any event, it's a great deal of differentiation, and you have to, avoid making minus sign errors and factors of 2 and so forth. And when you eventually do this, what you find is that the RR component of the Ricci tensor is given by a term involving the scale factor, the acceleration of the scale factor, the time derivative of the scale factor, then this curvature term, and then another term that also involves curvature. So if there's no curvature, it's fairly simple. It's 2a dot squared plus a double dot. The theta derivatives are also fairly simple. In fact, they're closely related. The phi derivative, the phi component is just sine squared theta times the theta component. And if you compute the curvature scalar, you get this expression here. So what are the Friedmann equations? Well, the Friedmann equations are what you get when you apply Einstein's equations. And again, you choose as your energy momentum tensor this simple perfect fluid model. And then what you find in the rest frame, things become pretty simple, because these u's vanish in the rest frame except for u00. And so then you get, it turns out you get this expression here. And the trace is equal to 3p minus the energy density. And this, by the way, is an important thing. This is, you can think of this as the inflation pressure. This is what drives, well, all right, let me not go off on that tangent. So Einstein's equations then give us this formula for the second derivative of the scale factor. And then they give us another equation for that. But one of the clever things that Friedmann did was to notice if you could subtract these two, you could subtract this one from that one, and then you just have an A dot equation. And so this is a first order nonlinear equation, and it is one of the Friedmann equations. This is probably the most important equation of cosmology. Well, this is a reasonable time to quit because we're basically out of time at 6:15. This thing on the left-hand side is the square of the Hubble rate, and the present value of the Hubble rate is what we call the Hubble constant. And so the Friedmann equation looks like this. Notice if k equals 0, we have something quite simple, that A dot squared is just the mass density apart from an overall constant, or the Hubble rate squared is the mass density apart from Newton's constant. And then even when you put in the curvature term, it's not that big a deal to change, although there is an A squared here, so it's not trivial. Anyway, we'll come back to that on Tuesday. There's a colloquium on Friday. I forget what it's about, but anyway, you should, as graduate students, you should go to all the colloquia, and in as much as they're available on Zoom, you can, attend the colloquium, and if the colloquium if you're learning something, you stay and watch the whole colloquium. If you aren't learning anything, then you can turn off Zoom or leave it on, but do something else, turn the sound down to 0 and just pretend to be there. But you should go, even if it's not in your field. It's important to learn as much physics as possible, and the colloquia are things the department goes to considerable expense to provide, at least when they're in person. They're places where you can learn a lot, and so I recommend that you attend all the colloquia. Let's see, there's something in the chat thing. Oh, yes, thank you. Somebody pointed out that Alan Guth is the physicist at MIT who invented inflation and coined the term inflation, and wrote a really quite lovely PhysRev D article back in 1980 or so on inflation, and it's a model of how to write physics articles. Really very, very nice article. Anyway, all right, I'm going to stop now and wish you all a good weekend, especially a safe weekend. Bye.